So today we're welcoming Jennifer DeHart, Anna Espinoza, and Isabel Suhr. They're going to be giving us a presentation on LROSE. So Jennifer comes from CSU, where she's been up there for about 8 years working on tropical meteorology topics. Prior to CSU, she did her PhD and master's at the University of Washington, working on tropical storm work and precip studies there, and did her bachelor's degree at the University of Michigan. Anna is at Unidata. She's been there for 3 years and has been working on LROSE as well as topics at Unidata. Prior to that, she was at Texas Tech University, where she did a master's on numerical methods, and she also works on the Science Gateway at Unidata. And then Isabel is a software engineer in EOL. She's been there for 8 years working with the various groups in the in-situ sensing facility. She did her bachelor's degree at Lewis and Clark College in Oregon, isn't it? In Oregon. And there she worked on Juneau ice field research, as well as she did an internship at NASA. So I'd like to welcome all three, and we'll start off with Jennifer.
Right, thank you, Bill, for the introduction, and thank you for coming to the seminar today. Today we're going to be talking about our LROSE Science Gateway, and I guess the title of our talk is Improved Accessibility and Community Knowledge of Lidar and Radar Data Analysis. And in addition to Anna and Isabel, I'd also like to thank Brenda and Julien, co-authors on this work, as well as other members of the LROSE team, so Mike Dixon, Michael Bell, Ting Yu, Wen Chao, Ana Del Moral Mendez. This was a group effort. So for those, I assume giving this talk at EOL, most people know what LROSE is, but for those who don't, LROSE is the Lidar Radar open software environment, and the goal of LROSE is to develop common software for the weather, LiDAR, radar, and profiler community. It's a joint project between CSU and EOL, and it's been funded by 2 successive NSF grants starting in 2016. Kind of the goal of LROSE is to have collaborative open source development with algorithms developed and supported by the community. And so if you look at this image on the right, I don't expect you to read it or understand all of these different points, but just if you imagine a workflow from radar data collection to display and or analysis, there's a lot of steps that are involved within that workflow, from quality control, derived products, et cetera. So within this kind of workflow, that we have over 400 applications within LROSE. So what do LROSE apps actually do? So if we envision this, or look at this image on the left here, this is from Precip, and oh, I lost my little. Okay, there we go. So this was from Precip in 2022. This is just some data from, I believe, one of the Mayu cases. So if you imagine this raw data, how do we get it to things that are more useful for scientists? And I should note that even to get the image on the left, a lot of LROSE applications have been used and a lot of kind of pre-processing. But if you take this more raw data and you do a lot of processing with other LROSE applications, you can derive things like precipitation estimates as well as 3-dimensional winds. And oftentimes these tools are used in conjunction with other open software tools, so PyArt, et cetera. Other capabilities of LROSE include making mosaics, finding the most likely hydrometeor using the NCAR PID algorithm, data display, as well as things like data conversion, storm tracking, and more. So we have a lot of different capabilities within the LROSE suite. And so LROSE is a really powerful software suite, but it's also really complex. So if one is to go and run any of our LROSE applications, you usually run it with a mixture of command line flags and a parameter file. And basically these two things set everything from data I/O to what specific scientific algorithm you want to use, what coefficients might be needed. So there's a lot of things and tuning that can go into the LROSE tools. So therefore, for a new user, there's can sometimes be, it can be overwhelming. Like, how am I supposed to structure this application? How am I supposed to set it up? So oftentimes we run a lot of workshops to help train the user community. But if we were, in the past when we've done this, installing and managing different LROSE versions wastes a lot of time. So we really want to be able to use those, 2 hours that we have on the most kind of pressing matters, not dealing with, does everyone have the right version? Can everyone install the application? So what we needed was quick and easy access to software data and materials, resources to support computationally expensive applications, terminal-like functionality, and the ability to edit text files, and then ways to visualize the data, whether that's within Python, our LROSE GUIs, or even just NCView when you want a quick and dirty look at something. So based on these needs, we've developed the LROSE Science Gateway, and NSF and other entities define a Science Gateway as a web-based resource for accessing data, software, computing services, and equipment specific to the needs of a science or engineering discipline. Within LROSE, we tested 2 different platforms for kind of providing a Science Gateway, one on an Apache Ervata framework, and then the other was a test run using the Unidata Science Gateway, which is basically a JupyterHub server. And after a bunch of testing, we ended up choosing the JupyterHub server as a Science Gateway because it mimics many workflows that scientists already use. A lot of people use Jupyter notebooks already. You can as well use terminal usage. You can edit text files. You can do all of this within this JupyterHub server. And so ours is hosted on NSF's Jetstream2 cloud supercomputer at Indiana University. And we obtained that through an NSF access allocation. And based on our prior testing, we actually established a formal partnership with software engineers, so Anna and Julien from Unidata, because they just had so much expertise deploying these JupyterHub softwares that we wanted to formalize that to simplify and accelerate our gateway development. And so on the right is just a screenshot of what our JupyterHub server LROSE Science Gateway looks like. And I believe the next section is Anna, who's going to talk about the actual implementation.
Thanks. Usually people clap after the talks. Of course, I'm just joking. So once again, my name is Ana Espinoza. Thanks for the introduction earlier, Bill. And I'm here to talk about the LROSE Gateway implementation. I'm going to discuss this section in about 3 parts. First of all, what is JupyterHub? What is containerization? How do they both relate to Kubernetes? This is the first section. Later on, I'll be talking about how we deploy Kubernetes. And then lastly, I'll be talking about some of the cluster architecture and the motivation behind some of those decisions. So this is going to be a little bit more tech talk than science talk, but I promise you it'll still be interesting. Cool. So a lot of the times when somebody says JupyterHub, you might have an image like this in your mind, but this actually is a JupyterLab interface. JupyterHub is actually all of the software that's behind that allows multiple users to access JupyterLab instances like the one you saw in that previous slide. You don't need to know what all of these different components do. Just know that each and every single one of them is special in its own way, and they are all necessary to run the full JupyterHub server in a functional way. So moving on from JupyterHub to containerization, I promise it is going to lead somewhere. A container is an abstraction that's similar to a virtual machine, except you don't have to virtualize any of the hardware, such as CPU or RAM, and you actually don't even need to run your own operating system kernel. It kind of piggybacks off of the host machine's operating system kernel. The images are built via Docker files. And in these Docker files, you can provide a set of instructions. And these set of instructions allow you to bundle software along with the exact environment. This is all the packages, libraries, and other dependencies needed for it to run. So this essentially leads, once you have built this container image, you can share it, and you have reproducible software and data analysis workflows. And JupyterHub has been containerized by the folks over at the JupyterHub project. And introducing Zero to JupyterHub with Kubernetes. So what is Kubernetes? You may have heard that word thrown around every now and then. It also is abbreviated to K8s. in case you ever see that in literature or out in the wild. And Kubernetes is a container orchestration engine. What that means in plain English is that it allows you to easily manage containers and the networking between them. It manages incoming traffic, what use as a server if nobody can access it, right? And you could also do stuff like provisioning cloud storage. There's a whole bunch of other things that Kubernetes can do for you. But the main aspect here, of course, is that you don't have to do a lot of this managing yourself. You allow Kubernetes to do it for you. And a Jupyter Hub is going to be deployed on top of Kubernetes. Once again, Jupyter Hub has been containerized. And you perform this deployment by using the Kubernetes package manager known as Helm, which is configured via a YAML configuration file. So here on the right-hand side, we have actually an older image which uses something called Jetstream2 in order to deploy the Kubernetes cluster on top of Jetstream2. And here we're just showing that the YAML config ends up going into Helm, which ends up deploying Jupyter Hub onto Jetstream2. But of course, how do we get a K8s cluster in the first place? Traditionally, we have used CubeSpray, which is a project that is a combination of two different technologies. One is Terraform, that's infrastructure as code, that's an IAC in parentheses there, which allows us to provision our cloud resources in such a way that it could even be version controlled, for example. The second portion of CubeSpray is Ansible, which is an IT automation technology. Once you have all of this cloud infrastructure, now you have to put Kubernetes on top of it. That's what Ansible will do for you. And importantly, I won't forget to credit Andrea Zonka of SDSC, that's the San Diego Supercomputing Center, for pioneering Jetstream CubeSpray, or in other words, a fork of CubeSpray tailored specifically for Jetstream2. Now, even though we have used Jetstream CubeSpray at Unidata for years and years now, there are definitely challenges associated with it. One is that it's slow to provision and scale. In this case, the scale means adding or removing more nodes, and this process can take up to an hour or more, depending on the size of the cluster that you are provisioning. Since CubeSpray is a project that's intended to be generalized to many platforms and clouds, this adds a lot of complexity, which makes it hard to explore, debug, troubleshoot, manage. So that's one of the things that was a challenge with CubeSpray. Upgrading to different CubeSpray versions is a long and painful process. I won't get into it, but you'll just have to trust me on that one. And lastly, no auto-scaling leaves resources idling. I did mention that in this context, scale meant adding or removing more nodes. A lot of commercial cloud providers, such as AWS, Amazon's cloud, provide auto-scaling functionality, so they will add or remove nodes automatically based on your incoming traffic. And so this isn't something that is possible with CubeSpray. However, we now have an alternative. As of late 2024, the Jetstream2 team ended up implementing something called OpenStack Magnum. And Magnum allows resources to be created or destroyed in an on-demand fashion via this cluster auto-scaling that we were severely lacking with CubeSpray. So now end users, which would be y'all, the visitors to the Unidata Science, or the LROSE Science Gateway, I'm forgetting what talk I'm giving here now, they could go and visit the gateway and be provided with powerful on-demand resources. And crucially, these resources are destroyed when they're not being used, which means fewer idling resources. This is, of course, good because we're being not just more energy efficient, but we're being efficient with our allocation at Jetstream2, which uses credits known as service units. Those are, of course, allocated to us, and they are, once you use them up, you're basically done for the year. So what does Magnum do, actually? It allows you to provision a K8s cluster very easily with a single command, and it gets provisioned in 10 minutes or less. And this is for essentially a cluster of arbitrary size almost. So while using CubeSpray, this would have taken an hour or more to provision the same cluster. Now with Magnum, we could provision it in 10 minutes with less configuration, less engineer interaction as well. And the way this is accomplished is that these nodes are pre-configured with Kubernetes, and once you launch them on the Jetstream2 cloud, they are just ready to be added to the cluster, and you could have a node scaled up within minutes here. And in addition to just this being a whole lot nicer, this command and its options can be scriptified for easier use, and of course this could also be version controlled, so that's really great. As I mentioned, new nodes are spun up in about 5 minutes. This includes both node creation time as well as any additional configuration time, which would include pulling of any more container images into the newly created node in order to run JupyterHub. Again, that is from the time you hit login on JupyterHub to the time where you have a fully functioning JupyterLab cluster or a JupyterLab instance. And then once the node has no pods, this is Kubernetes speak for a container. Once the node has no more pods, it will be destroyed after 10 minutes. Again, no idling resources means more efficient use in very many different senses of the word. So just to kind of summarize, CubeSpray has a long cluster creation time, whereas Magnum has a short cluster creation time. They have long scale times depending on the size of the scale, how many more nodes you're adding or removing. It could be equally as long, whereas under Magnum you could have short scale times. Under CubeSpray you didn't have any auto scaling, but Magnum you have auto scaling capable. And just remember this punchline. Again, it's faster. It's an OpenStack native workflow, less developer maintenance, less idling resources, which means more efficient use of our allocation. So this is actually, as I mentioned, newer kind of technology. We first started exploring this in late 2024, but it is still rapidly maturing. We've done a lot of different things with Magnum in terms of testing. Julien and myself over at NSF Unidata have been trial running a Magnum cluster for a few months now, including access by our new summer interns that started last week. We're, of course, looking for bugs. We're testing capabilities and all that good stuff. And at least at NSF Unidata, just to kind of demonstrate that this is something that's quickly reaching a mature state, we're going to plan on giving gateway users the option to have JupyterHub on top of Magnum or the traditional CubeSpray cluster starting this fall. And hopefully phasing out strictly to Magnum soon afterwards. We, in this case, we stands for the NSF LROSE team. We've already deployed a Magnum cluster in a workshop setting, which took place a few weeks ago, and which Jen will talk more about in a moment. And these workshop settings are very high stakes, meaning that there's little to no time to address any issues, and there were none. We did employ something called user placeholders in order to enable a rapid user spin-up. I'll talk about that in a second. And as I mentioned, Jen will be talking about this workshop soon. Additionally, just again to demonstrate how rapidly this tech is moving forward, Jetstream2 staff presented Magnum at the RMAC, the Rocky Mountain Advanced Computing Consortium conference that happened last week, and they have a 3-hour-long tutorial planned for Pierce in July later this summer. Okay, so last bit of my part of the presentation is going to be talking about our cluster architecture. I'm going to be taking kind of a problem to a solution approach. So things that we encountered along the way that we've learned from and then have been able to implement newer features. So what you see here is The basic Jupyter Hub architecture, you have your end users entering the Kubernetes cluster through something called an ingress. Again, you don't really need to know what all of these things are or stand for, but the bottom line here is it goes through one of these orange pods. This is called the Jupyter Hub proxy, which then routes end users to their single user servers. These are the JupyterLab instances. That's the image in your mind when somebody says Jupyter Hub. Again, this is kind of the default configuration. However, we learned during one AMS workshop that if you run too many computationally intensive tasks using this cluster architecture, you can actually crash the entire Jupyter Hub. And that is because all of these red single user servers are using up all of the compute power of this worker node, meaning the Jupyter Hub can't talk with people through the proxy, and everything just goes wrong. So this could lead to a big crash of the entire cluster. And again, that's exactly what kind of happened at AMS 2023. Everybody hit run on Samurai, and things went south. So to prevent that from happening, what we did is we dedicated an entire worker node just for these Jupyter Hub components. As I mentioned earlier, these are all special and necessary to make sure everything works well. Now, even if everybody is running computationally intensive tasks, that's all isolated from these Jupyter Hub core pods in orange. So everything is fine and dandy now, right? Well, unfortunately, if you have too many users scheduled on a single worker node, and you are using too much disk I/O or using too much CPU power or RAM, the compute performance is still going to suffer. So what we did instead is we started assigning each end user, every visitor to the Science Gateway, their own worker node. So that's great. Under the CubeSpray workflow, one thing that went wrong is if we only have one user on the cluster logged in, all of these other worker nodes are going to be idling away resources. Again, this is a CubeSpray problem. Under OpenStack Magnum, this will no longer be the case because now these worker nodes end up getting destroyed, and they could be recreated whenever we have new users come in. So that's how we ended up solving that. It was actually the folks over at Jetstream2. Thanks again very much. And earlier I mentioned that the scale time from login to you now have a new node to you are now in a JupyterLab interface is about 5 minutes. And we're all busy people. Sometimes 5 minutes is just way too long, right? So instead what we could do is we could spawn some user placeholder pods, and that's exactly what they sound like. They're a placeholder for a user that ends up, once somebody logs in, this pod will get kicked out and this node will be allocated just for that single person. And right here, we're only showing four green worker nodes, and these could be scaled to as many as you want. You could have as many user placeholders as you want to have the appropriate buffer zone, for example. One other non-cluster architecture challenge, this is now a feature, is that JupyterLab is typically limited to notebooks and command line interface apps. But many existing visualization tools, such as LROSE apps such as Hawkeye, they don't really run well in the browser, right? They're meant for a desktop environment. And this is a problem because now you're losing a big chunk of the LROSE suite of software. What we did is we ended up engineering a VNC solution here. So we have an X virtual frame buffer running in the background of this JupyterLab container, and it is accessed by an end user via a VNC client that is even proxied by the Jupyter Hub. That's a lot of tech jargon, but what you get in the end is just what you might expect, a desktop environment with Hawkeye running on it. So this is very useful. If you could see up here at the very top of the tab, you have JupyterLab on one tab, and you have the VNC client running on the other one. And so these two are actually linked. They have the exact same file system. They have all the same files, the same compute environment. And you could even run software via JupyterLab terminal, and it'll spawn here on the desktop environment side. So it's very neat. It's very cool. It's very handy. So just a quick section summary. What we've done is we've deployed Jupyter Hub on top of Kubernetes using the Helm package manager. OpenStack Magnum, which again is that new addition by Jetstream2, allows for easy provisioning and maintenance of Kubernetes clusters. And lastly, our cluster architecture and some of our features have been motivated by Science Gateway user needs. And I'll be handing this back to Jen. Thank you all.
All right, so now I just wanted to summarize some of the capabilities of our gateway with all of that back-end work, and it is a lot of work that's been put into place. So upon logging in to the gateway, I guess I should have stepped back and say we usually authenticate, or we prefer to authenticate using GitHub, just as a more secure way and also as a little bit less work on our end. Anyway, once a user has been authenticated and logs in, we now provide options of memory and processing resources. So low power, medium power, high power, basically varies, might be hard to see, but varies the memory from 4 to 24 gigs and CPUs from 1.5 up to 6 CPUs. For most instances, the medium power server choice is sufficient, but for Samurai, which for those who, I realize we didn't introduce Samurai, it's our multi-Doppler analysis package for retrieving winds. It's really computationally expensive, and so oftentimes that will require the high power server, but for most instances, the medium power server is sufficient. But in any event, we provide options now for the users. So again, this is just a snapshot of what our gateway looks like with one of the notebooks. So I'm just going to go through some of the other features that we have, but this is one of the main landing screens that a user will see once they log in. And as I mentioned before, it supports a wide range of tools, including notebooks, which again, a lot of our tutorials exist in. But a nice thing about the JupyterLab/Hub framework is that say you don't like notebooks and you prefer to run things via the terminal, there's a terminal option available in Jupyter Hub as well. Like we've had users that are like, I don't want to edit the text file straight. I just want to do it in VI. If you want to, people can have as much fun as they want with VI. And so it just opens a separate tab in this same framework. So it provides flexibility for the user based on their preferences, which is really great. As Anna just mentioned, we have the virtual desktop option that you simply can link with this icon that has the big V here for the VNC. So everything is provided within this system, which is quite useful. And again, just another snapshot of the virtual desktop option here, just showing a screenshot of NC view. Again, oftentimes if you're plotting within the notebook, it can get pretty tedious trying to create Python code for each specific instance. If you have a .NET-CDF file, sometimes NC view is just way simpler to just be able to click through all the different options. So it's good that we have different ways for visualizing that aren't quite so restrictive. So we also offer a variety of tutorials. So some of our tutorials, this is just a screenshot. I don't know if everyone can see the text, but it's just a screenshot from our kind of basics introductory tutorial. And so tutorials like this come with everything provided. Like we provide the data, all the commands are provided. All you have to do is go through and shift enter all the different commands, just giving you a basic overview of what LROSE applications do. Some of our scientific tutorials are ones like the one on the top right here. This is a dual Doppler tutorial. I believe this is a case from Alabama, Tingu, is that right? I think that was our Alabama case. Anyway, but this is just an example of the output you get after you run both Fractal and Samurai. Again, Samurai being our multi-Doppler analysis tool. So we go through things like that. We also go through QC using the Echo application, so running the NCAR PID, et cetera. And then we found with this tutorials where everything is provided, they're very great for workshops in the sense that they don't break easily because we've provided everything. You can just shift, enter, run everything, you get the same result. However, that isn't the best way for people to learn how to use the applications, which we noticed at some of our workshops. So we've started creating these what we're calling guided tutorials. And basically they have a bunch of tasks. We modeled these after a lot of the MetPy notebooks that come out through Unidata. And basically we have like task cells where we teach people how to work with the data to fill out the parameter files or use the command lines themselves. So we find that users will learn a bit more how to use the apps by help us laying out the different steps they'll need for setting up a workflow. So we also are developing those kind of tutorials as well. Oh, and this is, Isabel's gonna guest starring shot from Isabel.
Sure. So, as Jen said, community contributions are encouraged. So I am currently the example of community contributions. For the AMS workshop this year, I added a tutorial about how ISS processes wind LiDAR data. Some of the steps for that we use LROSE tools, and other of the steps we use our own Python software. And it's more of the everything is there and you just have to run it sort of tutorial for now. But one of the goals for this was to introduce more LiDAR processing in LROSE documentation, get the LROSE community used to that. As Bill would say, the L is for LROSE. And then also now we have a resource for people who want to look at or do something with or reprocess ISS LiDAR data. Now there's this example notebook of what we were doing and how we were doing it. And also the side benefit for me was having this to do for a workshop meant that I finally had a good excuse to package up some Python code that we've been using internally. So now other people can use our code to rerun stuff on our own data. And then as for a workflow, it's pretty easy. What you could do is fork the LROSE Hub GitHub repo and then create whatever Jupyter notebook plus whatever other files you need to include, and then submit it as a pull request. That's the link to the LROSE Hub. It worked pretty well for me. So I guess this is where I say maybe you want to do one of these too. That's all I've got.
So much clapping today. Yeah, so I think the thing we really want to stress is I and others in the LROSE team, we can only create so many tutorials. There's only so many things that I think users would want. So if people that use LROSE or think that a workflow would be useful, we want to encourage people to submit those tutorials. And the nice thing about doing it on GitHub is then you're marked as a contributor on the repo, so you get full credit. It just helps us expand and provide users with other things they need. And we're certainly happy to work with people on developing things and where to put data and stuff like that. But we definitely want to encourage the community contributions. Some use cases so far. We, at AMS this year in January in New Orleans, we had an LROSE workshop. The workshop in 2023 was actually hosted on the Unidata Science Gateway when we were testing out the software. Last year we had a pilot classroom exercise in Michael Bell's radar meteorology class at CSU. And then most recently we had an intermediate tutorial, and the scope was much narrower in that workshop, in that we focused on 3 groups of scientific parameters and tried to show how varying those parameters affected the ultimate scientific analysis. So it was more than just like, here is how you run the application. It's thinking critically about what parameter choices am I making, how does that affect my analysis, et cetera. So this was just an example of some of the parameters we were modifying. And basically the point of this image is just to show that we provided users with a range of values that they should test. And so they can go into the parameter file. You're only modifying 1 or 2 things at a time. And then you see what the analysis is. And we had this Google Doc or Google slide deck that all the users had access to, so they could put in their images using the different parameter combinations and then see how the analysis varied. So for example, I chose this slide because it's at this small, it's easier to see, but this was basically a use of thinning the data a lot versus thinning the data less. And so you can see by choosing the different parameters here where there's a lot of missing data, here things look more similar. But it was a way of just seeing what the parameter choices affect. So we also want to create more tutorials like this where we're teaching users, if you change the parameters in this way, this is how your analysis might be affected. So that's kind of the goal where we want to head as well, is thinking more critically about the parameter choices. And I also want to say the other great thing, kind of piggybacking off what Isabel said, the other great thing about all of these workshops is that in developing them, we actually fed back on our other research projects. So as Anna mentioned, all the work they're doing here is going to benefit the Unidata Science Gateway project as well. In our case, throughout all these workshops, we found multiple bugs in Samurai that we now need to fix. So it's been helpful in that way, like, and also hope as more users use things and are using things in different ways, we might discover more bugs. So it's a way to also get feedback on the actual core software itself and figure out where things can be improved. So now, and previously we've only had the gateway available for workshops, but we, as of last week, have advertised the standalone gateway that's available to any user that wants to log in whenever. And this is thanks to the auto scaling. So now we're not going to burn resources by having 100 nodes up. Now someone can log in, use their node, log out, it gets shut down, and we're not burning through our allocation. And as I said before, this is authenticated through GitHub. Once users register on a Google form, we can add usernames to an allowed list. And I'll have information on that in the final slide. And then I also created a user guide that can step through some basic, this is how you use the gateway, as well as where to submit bugs and things like that. And then, so we'll have this as a separate Jupyter Hub server, and then future workshops will be held on other Jupyter Hub servers. But so if anyone wants to use it, all you have to do is register and we can get you an account on the gateway, which is pretty exciting. So just to summarize, the LROSE Science Gateway provides educational tutorials to help the community develop skills with complex software. The server is hosted on Jetstream2 and provides the infrastructure required to run a variety of applications and workflows. Deployed on top of Kubernetes, and the creation of this auto-scaling technique has opened a lot of doors for us. On the LROSE side, we continue to explore how we can make the most effective tutorials and adding new content to that. And then finally, really want to emphasize the point that the partnership between EOL, CSU, and Unidata, getting all three teams together has really allowed for efficient use of all our team members' expertise. By having Anna and Julien deal with all the back-end development, it frees up the EOL team to focus on EOL, LROSE software development, frees up me to make tutorials and do my research. And I think this point is worth stressing even prior to the current funding environment. But yeah, just being able to have a team of different expertise has really been the only way that we could have made this gateway available. So I just really want to stress that point. Bringing in the different experts is really critical. So with that, I'll take any questions. I do have a QR code with the gateway access form, but then I was reminded by Kristen Rasmussen over the weekend that QR forms can be kind of dodgy. So you can also just email me. But if I swear that I made that QR code myself and it's not trying to steal your data. But we'll take any questions. Thank you.
Right, well, thank you very much. That was awesome. So we have online people can submit their questions through Slido, and I see there's one up there already. And then any questions in the room, I'll be throwing this around. And so please speak into the microphone if you do have questions so the online people can hear what's going on. So maybe we'll start with the online question. How do we sign up for dual Doppler and advanced tutorials?
Yeah, great question. So all the tutorials that we've used in prior workshops are hosted on the gateway, so anyone could go on at any time and run them individually. However, if you want to join for any future tutorials, workshops that we host, usually those are advertised on the LROSE users listserv. I'm not sure if there's a better way we could broaden kind of the advertisement, but that's typically where we've hosted or announced them. Yeah, but maybe that's a good point about broadening how we advertise that to people that we should work on. But yeah, all the tutorials are there.
Email Jen.
Okay, just spam my email inbox. Yeah.
Hey, Jennifer and team, great talk. I believe I'm one of the 3 original guilty parties come up with the LROSE. So I'm very happy to see where we're at today. My question is, you mentioned tutorial repeatedly in this gateway. Is this application only good for tutorial, or this is the direction that how a user can log on to a gateway and start to do serious work?
Yeah, that's a great question. Yeah, we thought a lot about this because like in an ideal world, you'd have the gateway and then you could bring the gateway to the data. Right now, you have to bring the data to the gateway. Each user is provided 10 terabytes of storage. So if you had like a low to mid-range size, or not terabytes, I'm sorry, gigabytes. Sorry, 10 gigabytes of storage. Yeah, wow. No, NSF is not giving away that much space. So there's 10 gigabytes. So if you have a small to mid-sized product, you could either upload the data or grab it through some other tool. And I should say we also have other software installed on the gateway. We have PyArt installed. Do we have MetPy? We should probably add that. So that could conceivably happen. The concern would be like if someone had a huge amount of data, that might be really cumbersome to bring it all there. But I think in an ideal world, that would be like a great step, is being able to bring the gateway to the data. So you're not spending all this time with data transfer. But right now, I'd say it's only possible with smaller to mid-size research projects, at least on the current Jetstream2 allocation that we have.
So does the team still recommend a heavy-duty user to install the whole package on their local server rather than?
Yes, I think so.
So my question is that my understanding is going through this gateway concept is to minimize the installation challenges. And I know this is a dilemma. You either bring the data to the server or vice versa. So I'm just wondering, any thoughts on how do we move into the future?
Yeah, and that's why I've often framed it in the context of workshops, because that's a case where you don't want installation at the beginning. I think you bring up a good point that we've certainly thought about. I don't know that we're necessarily have decided on how that might work. But I agree that that's the idea. And I will say too, continually improving the installation, Mike and others are working on a Conda Forge packaging for LROSE, which a lot of people already use Conda or Mamba. And so that would simplify the barrier as well. And then it would be even easier to install on things like other supercomputers. So yeah, it's an important question. It's a good question. I don't know that we have a specific solution identified. I don't know if Anna or anyone else wanted to comment on that, but yeah, I think it's a challenge, but it's a really important point. Yeah.
Thanks. I appreciate the tech talk. So a node in the cloud, the Kubernetes, is just a container instance.
This is not a question.
Yeah, sorry for not making that super clear. A node in this context is just a virtual machine that's created by the cloud provider Jetstream2.
So it's a full virtual machine.
It's a full virtual machine, and the containers will run inside these nodes.
Do people have SSH access?
They do not have SSH access. They have access to the container that is running JupyterHub, or the JupyterLab, I'm sorry.
Which includes all of the LROSE software.
Exactly.
And NetPy packages and all that.
Yes.
So when
correct.
JupyterHub gives them a terminal, they have access to all those tools.
Yes.
Is there any thought to using that environment to also build LROSE? I mean, how much has LROSE been able to democratize the actual collaborative software development as opposed to just the user access?
Yeah, that's an excellent question. As of a few weeks ago, maybe even last week, I'm losing track of time here, we're actually doing an LROSE nightly build on the gateway. So very, very soon, any gateway visitor will be able to access basically the cutting edge version of LROSE. we could potentially provide the capability to have them build it themselves, but I imagine that if you know how to do that, you're probably not the intended audience, as kind of we were just discussing. But yeah, it's certainly possible to set up an environment where you can build LROSE on the gateway.
Well, so I'm right, because I'm curious about the open source part, not like the people who are going to develop the community algorithms and extend LROSE.
Sure, yeah.
For them, it's still the hard case of install, all the dependencies on some local machine and do a build and learn how the software builds, and as opposed to I log into somewhere where it's already possible to run a build, and I just change a source file and I can see my actual change, test my actual changes there.
Yeah, that's an excellent idea, and we will definitely keep that in mind. I love that suggestion.
I'd be curious to see if that helps, right? Because we all have that kind of issue of how do you
Right,
make
yeah,
it really
yeah.
easy for people to change not just use the code, but actually develop.
Yeah,
the code
exactly. We
to
could
their
have
needs.
some kind of developer profile on the gateway is what you're kind of suggesting, right?
Yeah.
Jen?
Thanks.
Yeah, the other thing I'd add is, the challenge that we've always encountered with LROSE is that most of the code's in C++, and most people are no longer, or I'm speaking here as a scientist, not a software developer. I know software engineers are much better C++ coders. But that's been our challenge, is that we have not had as many contributions, in part because people don't know from the scientists. So oftentimes it's a more labored process of publishing a method in a paper or working with Mike directly. But that is a good point about having like a separate profile, like a LROSE dev or something, for people that do have those technical skills to do that. Yeah. It's a good suggestion. I don't know if Mike or Brenda wanted to add on to. You don't have to if you don't have any cup, but.
I think you hit on the important point. So there's kind of two users, sort of. There's the contribution to the code base itself, but that's C++, and Isabel is a contributor, which is great. But we don't have that many contributors. But then there's also the science side, the contributions to the tutorials, and then that's more Python and that. And so we're seeing, I don't know, maybe we see, I think they're, I don't know, maybe it's equal right now as far as contributions, but it might be easier it's definitely easier for scientists to contribute Python code, so the tutorials and that, and not the back end C++ code. I mean, is that what you run into too, Gary, with stuff?
We don't try and do open source.
Oh, you don't, oh, okay.
It's just too difficult to get people
It is.
to have traction and want to contribute.
One other thing I have thought of is that, again, it's not necessarily contributing code, but it's like having the gateway is a really reproducible way for sharing like bug reports, because you could have your notebook or have all your parameter files data within this thing and then send it. And as admins, we actually have access to everyone's server, which we use that power very appropriately. But that is one way that you could go in and see, like, reproduce exactly their bug and have fewer like Google, links sharing data and stuff like that. So that is one other use case I've thought of, is using it as a way to report and or document bugs and or show improvements. So another way of contributing, even if you aren't directly coding. But.
Oh, Gary.
I'm going to stick on tech unless you people ask questions. Any consideration of switching to cloud data formats, ZAR and such, more friendly? Or is it all still NetCDF and
It is NetCDF. I'm looking at Mike.
And NetCDF is proving efficient enough for a cloud deployment?
We really haven't tried to scale it up. I mean, the tutorials just, we put, either put data there or the Python code downloads the data from the cloud somewhere to run those examples. So we're just using NetCDF. ZAR, I don't have much understanding of it, but what I do know is that you've got to kind of repackage your data set into ZAR, right, and upload it. And so, you could do that for a tutorial, obviously, right? But that would require quite a lot of technical smarts on the part of the user just to be able to do that piece, right? So I'm not sure it buys you that much if you're, unless it's like if it's always a single, if the data is commonly used, but what if everyone has different data? And, like each user needs a different data set, then you've got to generate the ZAR database for that, for each one individually, right? So is that efficient? I don't know if the extra efficiency in terms of reading it is going to really be, worth all the effort to create the thing in the first place. That would be my guess, right? It seems to me that the whole ZAR thing is great if you're uploading something that's going to be used a lot of times. But if it's only going to be used by one user, I don't know. Yep. And on the, if someone wants to contribute, then I think just building LROSE on your local, computer and developing there it's not a high bar anymore, right? It's pretty easy to build. But for the tutorials and the workshops and so forth, we're aiming at the educational, we're sort of thinking of, meteorology, courses and helping, professors to, run examples where the thing is available to everyone in a pretty simple way. So, that's been our kind of main focus so far.
So we have another question online from Ruza Islam. It's if we're talking about NextRad scale data processing for a few days, for example, do we need to watch out for anything?
Yeah, I think the first, I'm forgetting I'm trying to think back to my other projects where I've looked at a lot of NextRad data. I think the big thing I would be concerned about is like the data set size, because not only is it the size of the original data, but then you'll have copies of any intermediate data as well as the final output product. So that could, depending on how many days, and I guess this kind of gets back to Wen Chao's question about like use cases. And again, ideally, it would be great if like we could provide this resource and you could do whatever processing you wanted in the cloud. At the time being, at the current scales we're looking at, it is more of like an educational, so like prototyping or learning how to use the software. But certainly, like we would love to be able to provide like a cloud where you could go and just run the data. So I think that would be, I would say computationally, depending on the program, like especially most of like the RADX apps with NextRad, I wouldn't really be too concerned about the compute power. It might just take a little bit longer depending on how many files there are. My concern just right away would be how big is like all the data that would that take up the entire 10 gigabytes. I guess that would be the, yeah.
I could So, a day of NextRad raw data is probably a gig, right?
Okay.
So if you did 3 days, then it's 3 gig in the raw, and then there's probably another 3 gig in the, the converted. So now you're up to 6. So you're starting to run into problems with the data because the data storage is the expensive stuff on the cloud, right? Rather than, the compute. But that probably will change over time, right? I mean, what if we get if Jetstream becomes 10 times bigger, then that becomes pretty feasible. So it might be that we're not that far away from being able to do that. But right now, you'd probably need to do just 1 day at a time and then delete your day, delete some of it and grab another day. But you can download the NextRad stuff from AWS pretty fast and just in probably half an hour or something and then run it. So it could work.
Yeah, I would say Jetstream2 in particular is like one of the more expensive like thinking of all the NSF access resources, it's like one of the more expensive for storage. Like I think Stampede 2 and the other supercomputers, the storage is a little bit cheaper because Jetstream is meant more for, I think, like educational applications. So, yeah.
Right. Well, I'd like to thank you very much for giving this presentation. And can we have another round of applause?